In today's video, we'll be taking a look at the first free response question from the 2005 AP Physics Mechanics test. This question involves questions about air resistance and terminal velocity. So it's mainly balls up in the air, going up and coming back down, and questions all about them. So the question we have today is a ball of mass m is thrown vertically upward with an initial speed of v0. It experiences a force of air resistance given by F equals negative kV, where k is a positive constant. The positive direction for all vector quantities is upward. Express all algebraic answers in terms of m, k, v0, and fundamental constants. This question had 5 parts on the exam, so we're going to take time in answering each one thoroughly. So before we begin the first part of the 5-part question, we want to draw out the system which is acting on the ball. So first we want to add a ball of mass m to our drawing, which is represented by the red circle. So the first force that should be recognized as acting on the ball is the force of gravity, which we'll use an orange arrow to depict. The force of gravity is always pointing down towards the earth whenever an object such as this ball is in the air. It is a conservative force which will never change. It will always be 10 meters per second on Earth, but we're only worried about the force, not the actual quantity. And then the second force that we're going to actually have in this system is the drag force or air resistance. We're going to call it drag force for this example, and we're going to make it the color green. When the ball is going upwards, the drag force will be pointing downwards, and when the ball is coming back down to Earth, the drag force will be pointing upwards. The drag force always acts in the direction opposite of the motion of the ball. So if we were to draw the real system, as we can see here, the ball of mass m exists, and now there's only the force of gravity and the drag force initially going downwards because the ball is going upwards in the air. So with this system in mind, let's move on to part A. Part A asks, does the magnitude of the acceleration of the ball increase, decrease, or remain the same as the ball moves upward? And we have to justify our answer. So we are going to take the system that we just drew, and we know that the sum of the forces, or F net, which will be used later, equals ma, which is mass times acceleration. This is Newton's second law. And we know that the forces acting from earlier are the drag force and the force of gravity. So the sum of the forces in this system would be negative kV plus mg. And they are both negative because as the ball is going upwards, gravity and drag force are acting in the opposite direction of motion in this case. So they're both negatives. And so we know negative kV plus negative mg equals ma. So now that we know the equation for the forces acting on the ball as it moves upward, we're going to take a look at this diagram which depicts how the forces change as the ball moves upward. So in the 5 positions, we can notice that the force of gravity does not change because it is a conservative force and remains the same on the ball no matter where it is. But the higher that the ball goes, the less the drag force becomes in the downward direction. This is because as a ball increases its height to the apex, it decreases its speed to 0. And because drag force acts as opposite to the initial velocity or opposite to the direction, the drag force also goes to 0 because there's less motion for it to repel. So, with this in mind, and the thought of how the equation is negative kV plus negative mg equals ma, we can see that as the ball goes upwards, the total force becomes less and less. And because F equals ma, as F becomes smaller, A will also become smaller proportionally because m does not change. So moving on to part B, it asks us to write but not solve a differential equation for the instantaneous speed v of the ball in terms of time t as the ball moves upward. So what we want to remember here is that kV will remain negative as well as mg because as the ball is moving upwards, both forces are acting in the opposite direction of motion, as we have seen in earlier examples. So we're going to pull the diagram that we've had up earlier, just as a reminder for us, as mg and kV are both acting in the negative direction. And from earlier, remember that the sum of the forces equals ma. So we remember that F net equals negative kV plus negative mg. We also know from basic kinematic equations in earlier physics that the equation for A is the derivative of velocity with respect to time. So in the end, essentially, the equation is sum of forces equals mass times acceleration, where we use the differential equation for acceleration to plug in for A, and we use the two forces, which are kV and mg, on the sum of the forces side for the actual equation to take shape. And moving on to part C, it asks us to determine the terminal velocity of the ball as it moves downward. So first we ask, what is terminal velocity? So we know a ball falling at terminal velocity, the forces are equal, resulting in a zero-sum force, where ma essentially equals 0. So what does that actually mean? Well, as you can see in this diagram, as the ball moves downward, the speed increases due to the gravitational acceleration. But, as we learned earlier, as the speed increases, the drag force also increases in the opposite direction. So any object that is falling in through the air will experience a point of terminal velocity if dropped from a high enough point. This is when the drag force equals the gravitational acceleration, canceling out the two forces, creating a singular velocity at which the object will be traveling. There will be no more acceleration in the downward direction, and there will be no acceleration in the upward direction. The ball will essentially be moving at a constant speed. So keeping our third drawing from the previous example, we can see that the drag force equals the gravitational acceleration by the bars through the two arrows, which means that they are equal. So from what we learned earlier, we know F net equals kV minus mg, but in this case kV is positive because it is acting in the upward direction, whereas mg is still acting in the downwards direction, as gravity always acts in the downward direction. We also talked earlier about how at terminal velocity, ma equals 0. So our next equation, we have 0 equals kVt, Vt stands for terminal velocity, minus mg. This is essentially saying that the forces are equal. So then if we wanted to solve for terminal velocity, we would add mg to both sides and then divide by k to isolate Vt for our final equation to be terminal velocity equals mg, which is the force of gravity, divided by our constant k from earlier. And that brings us to part D. Does it take longer for the ball to rise to its maximum height or fall from its maximum height back to the height from which it was thrown? And we have to justify it. Here we have a little drawing of the forces acting on the ball just before it hits the apex, at the apex, and just after the apex. So as we can see, as the ball is rising, the force of gravity and the drag force are both acting in the negative direction. At the apex, there is only the force of gravity because there is no speed, which means there is no drag force. And as the ball starts moving back down towards the earth, we can see the force of gravity is still acting downwards as a conservative force, and now the drag force is acting upwards in opposite direction of the motion. So with this, we can see that there's more total force acting downwards on the way up than total force acting downwards on the way back down. And as there is more force on the way up, this means that there's a greater negative acceleration, which means the velocity will slow to 0 much quicker than on the way back down, where because there is less force acting downwards, there will be less downwards acceleration, which will increase the time that it takes for the velocity to increase. So with that being said, it means it will take longer for the ball to fall and quicker for the ball to rise and hit 0 and start falling back down. And then finally we have part E. On the axis below, sketch a graph of velocity versus time for the upward and downward parts of the ball's flight, the entire motion of the ball from start to finish. There, TF, time final, is the time at which the ball returns to the height from which it was thrown. So this is essentially the end of the graph where the ball is up and then it comes back down to the person who threw it. So as we can see here, we've sketched our basic graph. It looks like a T-graph where we've got some positive, a negative, this where the y-axis is acting as the velocity and the x-axis is acting as time. And we have tick marks for 1/4, half, 3/4, and then the end is final. So we know from earlier that it takes less time for the ball to reach its apex than for the ball to fall down to the ground. So what we need to do is we know that the graph will cross the x-axis before the halfway point, because the velocity will be 0 before half of the time is done, as the ball rises quicker upwards than it falls downwards. And then we know the shape of the graph to be this way because the speed is decreasing at a decreasing rate as it approaches terminal velocity. And the end of the graph should be horizontal because this is indicating the ball reaching its terminal velocity, at which the change in velocity would be 0 and it's just a constant velocity. There's no acceleration. And the apex, as seen marked on the graph, is before halfway because the velocity of the ball reaches 0 before halfway, since it rises to its apex quicker than it falls from the apex back down to the ground.